This is A2Further maths, and we're in Unit 8 hyperbolic functions, and we're then just taking a look at some of the identities. So many identities exist for hyperbolic functions, and these have similarities to the ones you've already met in trigonometry. Here are some examples. In nearly every case you can prove hyperbolic identities by using the definitions kind of given in the first part of the chapter. So we're going to try and prove that cos squared minus sine squared equals 1. I'm going to set this one up as difference of two squares. So that's going to give me cos x plus sine x upon cos x minus sine x. So what is cos x? We know cos x is e to the x plus e to the minus x over 2. Then sine x is e to the x minus e to the minus x over 2. E to the x plus e to the minus x over 2 minus e to the x minus e to the minus x over 2. So what do we have here in our first bracket? E to the x over 2 plus e to the x over 2. That's just going to be, that's half e to the x and half e to the x. That's just e to the x. And can you see then that actually the e to the minus x's are just going to cancel? Because you have e to the minus x over 2 minus e to the minus x over 2. So this first bracket just gives us an e to the x. Second bracket, e to the x minus, sorry, e to the x over 2 minus e to the x over 2, so they cancel out. So in this case then, we end up with a e to the minus x over 2 minus minus e to the minus x over 2. So here we just get an e then to the minus x. Let's multiply these. So what do? We add the two powers, and you get e to the 0. And that, of course, then gives us 1. Sorry, you missed that wee last line there. That gives us e to the 0 because we add the two powers. X plus minus x gives us 0. E to anything to the power of 0, then it's going to be 1. So two further identities then can be easily deduced from this identity. We know cos squared minus sine squared. Slightly different, remember, than cos squared plus sine squared equals 1. Much like the associated trig identities, if you divide by cos squared x, you obtain 1 minus then sine squared over cos squared, which gives us tan squared, and then 1 over cos squared is sec squared. So it's 1 minus tan squared x equals sec squared x. And then if x is not equal to 0, divided by sine squared gives us, so we have cos over sine gives us cos squared minus sine over sine is 1 equals then 1 over sine, which is cosec squared. Next we identity then, this is our example 2. So it asks us then to prove that cos x plus y equals cos x cos y plus sine x sine y. So let's see if we can get this one tidied up. Again, I'm just going to change everything to take the right hand side here. So this is e to the x plus e to the minus x all over 2. E to the y, sorry, plus e to the minus y all over 2 plus then sine is e to the x minus e to the minus x over 2 upon e to the y minus e to the minus y all over 2. So I'm going to stick this all in a massive big square bracket. And the fact that we're multiplying this by this, hope you can see that's going to give a quarter, that's going to give a quarter, so I'm going to take that quarter at the front, and then we'll tidy it in from there. So what we're going to have, so I've kind of taken out the bottom bit, I hope you're okay with that, and in fact we're going to do FOIL then from here. So e to the x times e to the y is going to be e to the x plus y, then outer plus e to the x minus y, inner plus e to the y minus x, and last plus e to the minus x minus y. Here then e to the x plus y, and then outer is going to be minus e to the x minus y, inner is going to be minus e to the minus x plus y, and last then is minus times the minus, so it's a plus e to the minus x minus y. So some things are going to cancel. E to the x minus y minus e to the x minus y, e to the y minus x minus e to the y minus x. And so what are we left with? Well, e to the x plus y, e to the x plus y. So two of those and then two of these. So that gives us a quarter 2 e to the x plus y. And those are both pluses as well, then plus 2 e to the minus x minus y. The fact that there's 2 there and a quarter outside, we can go for half e to the x plus y plus e, and then we'll take the minus out here, minus x plus y, and hope you can see that we're pretty much there. And that gives us then cosh of x plus y. So that's that proven. By writing x equals y equals a, we get then our kind of double angle equivalent. So cosh 2a equals cosh squared a plus sine squared a, which is another well-known hyperbolic identity. And then example 3, find an identity for sine 2a in terms of cosh a and sine a, hence find an identity for tan 2a in terms of, tan 2a in terms of tan a. So sine 2a is going to, just using the formula for sine, is a half upon e to the 2a, sorry that's an a, it should be a capital A as well, I got a hams here, 2a minus e to the minus 2a. So where am I going to do this? I suppose I could do, because this is squares, you could do difference of two squares here, so I'm going to write down a half e to the a plus e to the minus a upon e to the a minus e to the minus a, and hopefully you can see them are pretty much here. If I take this out, then can I give it a 2 here and then bring a couple of halves in? E to the a plus e to the minus a, just move it up slightly, all over 2 e to the a plus e, sorry that's minus, seriously, minus e to the minus a, and then that's all over 2, and we can see then that that gives us 2 cosh a sine a. So that's the first bit then that we've been asked for. Let's take a look then at the next bit. Tanh 2a we're asked for, so let's see if we can make something out of that. Tanh 2a we're going to write as sine 2a over cosh 2a. That's going to give us 2 cosh a sine a. We've just used that from the thing we've just done on the previous page, and then what we also had on the previous page, the first example, was that cosh 2a is cosh squared a plus sine squared a. Let me tidy that up. Let me see, what am I going to do? I'm going to divide top and bottom by cosh squared a. Again, it's hard to see how you're coming up with that, but just with, I guess, a bit of practice you get an idea of these. So cosh a over sine a over cosh squared a. Bear with me, I promise it'll get nicer looking in a second. And then on the bottom we're dividing both bits, so it's cosh squared a over cosh squared a plus sine squared a over cosh squared a. So how does that tidy things up? If we divide here by cosh squared a, this goes and this goes, so we end up with 2 sine a over cosh a. Should have an h in there, forgetting these all over the place. So that's actually the same as 2 tanh a. So top line then is 2 tanh a. Cosh squared over cosh squared, that's an easy one, that's 1. And then sine squared over cos squared, that's tan squared. And that's our identity then for there. Wee bit then about Osbornes Rule, very straightforward little thing really. You notice there is much similarity between trig identities and hyperbolic identities. Many are of the same form with signs changed, but not always. For example, cos squared plus sine squared equals 1. However, the hyperbolic version is cos squared minus sine squared equals 1. Whereas this one's just exactly the same. Sine 2a equals 2 sine a cos a, whereas sine 2a equals 2 sine a cos a. Osborne's rule gives you a simple way to remember when to make a sign change when moving from a trig function to its hyperbolic counterpart. Here's the rule. The rule is to replace each trig function by the corresponding hyperbolic function and change the sign of every product or implied product of two signs. So there's a product of two signs, for example, because that's sine times sine. So we have to change the sign there to a minus. That's effectively the rule. With a couple of examples over leaf, we'll do those, and that's this video then finished. So give the equivalent hyperbolic identity for the trigonometric identity. So we have cos 2x equals 1 minus 2 sine squared. So we're going to change that. You see the implied product, the product then of two sines. So we're going to change that then to a plus. So it's going to be cos 2x equals 1 plus 2 sine squared x. That's what we have to do. Tan, so where they're going to go, tanch of a minus b is equal to tanch a minus tanch b all over. Give me 1 second here. Sorry, I'm back. And then along the bottom, this bit's quite important. So it's then going to be 1, and we're changing this to a minus. So can you see why? This is what we mean by the implied product, because tan is sine over cos. So it's sine over cos times sine over cos. So that's our implied product then of two sines. So that's then the instance whenever we change the sign. That's why we've done this example effectively. So it's tanch A, tanch B. And again, I've written in beside, you probably want to do the same, as there is an implied product of sines in tan A, tan B. Hopefully you can see then where that's coming from.